Okay, let's begin.
Why would you pass up these opportunities to be ahead of the game?
Right, last time we were learning how to count. Let's just do a quick recap on what we've seen so far. We saw something called the multiplication rule. Several ways you can state that. A, B sets, the size of A is n, the size of B is m, then the total number of AB is going to be n times m, where A comes from the first set and B comes from the second set. Another way to state this, aka if an experiment has m stages and the number of outcomes for the ith stage is n sub I, then total number of outcomes of the whole experiment is going to be equal to the n1 times the n2 times the n sub n. Okay? So if the first stage can happen in n1 ways, the second stage can happen in n2 ways, the third stage can happen in n3 ways, etc. You would multiply all of those numbers, and that will tell you how many total ways the entire experiment can go. That's called the multiplication rule. We then saw one other thing. So one major thing was the multiplication rule. It's a super important rule. The second major thing we saw was when counting tuples. So let A is a set. Say it has n things in it. We want to create all r-tuples. That means it looks like coordinates, a1, a2, dot, 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 all the way to r of them, without restriction. So there's no restriction on what you can throw into each coordinate. You can pick a guy, you can pick him again. You're allowed to repeat things, you're just doing it in a certain order. Total number is going to be, n times n times n r times, which is n raised to the r power. That's how many possible coordinates of length r you can make. Here your r is of course assumed to be less than or equal to n because it doesn't really make any sense otherwise. There are going to be reasons why it won't make any sense. And finally, we saw the idea of a permutation. This is counting tuples, but repeats not allowed. And of course, because we're counting tuples, I'll just re-emphasize here, order matters. The order in which you're writing these things down will matter. So we call that P n r, and that was just going to be the product of n times n minus 1 times n minus 2, multiplying all the way down to n minus r plus 1. Now, I don't remember if I mentioned this, but what you want to take away from this is the number of ways to choose R objects from N objects in a certain order. Without repetition. Those are going to be important. The fact that it's in a certain order and it's without repetition. Right? If you're allowing repetition, it looks like this. If you're not allowing repetition, it's going to look like this. And why was it called a permutation? So, if we consider P of n, right? So I want to make a tuple of size n from n objects, so I'm choosing all of them at some point, but I'm just picking things and putting them in a certain order. That, of course, is going to be equal to n times n minus 1 times n minus 2, dot, 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 all the way down to n minus n plus 1. So what we get is the product of all the numbers starting at the integer n, positive integer, multiplying all the way down to the integer 1. Now there are a couple things I want to tell you about that number. This number is called a factorial. Okay. So if you start with a positive integer n, and you multiply all the integers starting at n going all the way down to 1, you said you have found n factorial. So n times n minus 1 times n minus 2 dot, 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 all the way down to 3, 2, 1. And here's the notation that we use for this. So this is the notation that I'm telling you here. It's n! You say it with a lot of excitement, and you write an exclamation point, and that means n factorial. So, for example, I can say, what is 3 factorial? Well, that is just 3 times 2 times 1. That's the number 6. What is 5 factorial? Well, that's just 5 times 4 times 3 times 2 times 1. That's 120, etc. And this is called 3 factorial. That's called 5 factorial. That's the first thing I want to tell you about this particular number. And here's what it means. N factorial equals the number of ways that you can arrange n objects in order. Right? Because essentially what you're doing is you're creating a tuple where you're choosing everyone from a set and you're putting them in order without repeating. So if you can have n choices for who to put in the first position, then you have n minus 1 choice for who to put in the second position, and so on and so forth. You end up with n positions being filled, where by the time you get to the last position, there's only one guy that you could pick to put in that position. So it's called a rearrangement. And so rearrangement, the word permute means rearrange. And that's why it's called a permutation. This number helps us figure out how to actually arrange a bunch of things in order in different arrangements. So what does it mean when I say 3 factorial? So what does, say, 3 factorial mean? Well, one, it means first that equation, 3 times 2 times 1, which is 6. But also what it means is if I have a set with 3 things in it, and I want to know how many ways can I arrange those 3 things. So I can put the A first, then the B, then the C. Or I can put the A first, then the C, then the B. Or I could put the B first, then the A, then the C. Or I could put the B first, then the C, then the A. Or I could put the C first, then the A, then the B. Or I could put the B first, the C first, then the B, then the A. Notice that that is all the total number of arrangements that I can make with these three objects. There are 6 of them. There will be no more. So if someone asks me, well, you have 5 things, how many ways can you put them in a different order? 120 ways. Now I don't need to actually list all 120, but I know that's how many there are going to be, right? And that's what combinatorics is, counting without counting. I can kind of know how many things there are without individually having to list them out, because that's not very efficient. So PNR is called a permutation. It tells you how to put things in order without repeats. And if you choose all of the things from a set, you get what the number we call n factorial, and that is the number of possible rearrangements of n objects. Also, FYI, we declare, we decree, let's just say, more politely, by convention, 0 factorial is 1. Now there are many reasons why we want it to be 1. First of all, you can think of it in this language. How many ways can you rearrange no objects? 1 way, it's nothing, it's what it is right now. That's all it'll ever be. Also, 1 factorial would mean the number of ways you can arrange 1 object, there's just 1 of them. 2 factorial, the number of ways you can arrange 2 objects, 2 of those, and so on and so forth. And this falls in line with a lot of other patterns that we like, and so that actually makes it makes sense. So even though technically by the definition I gave you for a factorial, that doesn't make sense to say 0 factorial, by convention we define it to be 1 for many reasons. Here's another way to write PNR, and this is probably the formula that you would see in a textbook. And this is also going to show you why, another reason why it makes sense to make 0 factorial 1. There are many reasons, but here's another one. If I have PNR, we know that this is n times n minus 1 times n minus 2, all the way down to n minus r plus 1. What we can do is we can multiply and divide by a convenient thing, like math people like to do all the time. Just continue this pattern. So the next one down would be n minus r, then n minus r minus 1, dot, dot, dot. Eventually we'll get down to 3 times 2 times 1. But I can't just multiply by something out of the blue, so we divide by it again. N minus r times n minus r minus 1, all the way down to 3, 2, 1. Now what you would notice is that now the numerator looks like, what does the numerator look like? It's the product of all integers from n down to 1. Well, that's n factorial. And the denominator looks like product of all the integers from n minus r going down to 1. That's n minus r factorial by our definition. And so what we have here is that p and r can be computed by n factorial divided by n minus r factorial. And one thing you can note here, this is just a side statement, so that's another definition. Chances are if you look in the textbook, that's the definition they're going to tell you. But it comes from them counting tuples and just rewriting it in terms of factorials. one thing you can notice here as a side statement we know that P and N is N factorial with this formula. Your P and N is going to be N factorial divided by N minus N factorial, which is going to be N factorial divided by 0 factorial. So now you might think, well, what would I make 0 factorial to get these two to actually work out? It has to be 1 for them to work out. Couldn't define 0 factorial to be 0, we'd get this thing undefined. It would be impossible for us to figure out what P and N is, but we know it's not impossible. It makes sense that 0 factorial is 1. Now, let's talk about another situation. What if I want to choose things in a way that order does not matter? This might be true. I might need it, and we will look at examples where we will need it. So let's look at that. Choosing when order does not matter. So here, convenient to use sets to think of this idea instead of tuples. Because sets, we know, have no inherent order. Tuples do. So now, let's consider this question. If A is a set of size n, how many sets of size r can we create where your r is less than or equal to n? Okay. So I can ask the question, for example, if I have a set with 6 things in it, and I want to create sets with 3 things in them that I'm picking from that 6 sets, how many possible 3 sets could I create? Now, once you're creating a set, you're ignoring order. You're also automatically ignoring repeats. So this order doesn't matter, and repeats won't matter either. So let's illustrate this. Example 1. Let's say your A is a set ABC. How many sets of size 2 can you create? Without order. Right? I have 3 things. I want to pick 2 things at random and create another set. I want to create a subset of A in technical language, but the subset must be of size 2. How many such subsets are there? Well, we can actually list them, enumerate. I can create a set with A and B. I can create a set with A and C. That's that. I can create a set with B and... Now once I put B, I can't put A because that would overlap with this. That would be the same thing. So I can put B and C. Anything else? That's it. There are 3 possibilities. You think you can come up with a formula? To get 3 as the answer, yeah.
Is it n factorial over n factorial times n
No. That's close. The n in the denominator shouldn't be there. Should be an r instead. Okay, so this one we can actually count it individually, but let's get larger. A equals 6 things. A, B, C, D, E, F. How many sets? of size 4. Now, there are going to be more than 3. More than I probably care to actually write down. Let's figure out without listing. Sometimes listing is important, which is why every now and then I'll throw an example where I literally write everything out for you. But sometimes the numbers are going to get so big that you kind of don't want to have to deal with it. So, how are we going to figure that out? Well, consider one possible subset of size 4. Let's say I take A, B, D, and F. Okay? That's one random subset, right? Now, here's how we're going to think about this. If we were to create tuples, how many would we be able to get from this set?
24.
Huh?
24.
How'd you get 24?
24 factorial.
It's going to be 4 factorial. Why is it going to be 4 factorial? Because corresponding to this set, I could create a tuple that just leaves things in order, or I can create another tuple where the B is first, the A is second, D, F, or I can da-da-da. Basically what I would do to create tuples is I'm just going to count the different arrangements that I could make of these 4 objects. There are 4 factorial total tuples. Now the thing is, we know how to count tuples, so let's actually use this to our advantage. So this means if I take the number of 4 sets of size 4, how would those compare to the number of tuples? So like 4 tuples. Well, we know that the number of tuples are going to be bigger because for each one set, there will be multiple rearrangements. In fact, in the case of 4, I know exactly how many arrangements there will be. If I take the number of sets multiplied by 4 factorial, I will get the number of tuples. For every one of those, I have 4 factorial of these. So this means the number of 4 sets is going to be equal to the number of 4 tuples divided by 4 factorial. Well, what is the number of 4 tuples? Well, that is now asking the question, well, if I have a set of size 6, how many tuples of size 4 can I get without repetition? Well, that is literally P of 6, 4 over 4 factorial. Now, that is going to be 6 factorial over, well, 6 minus 4 factorial, using the formula that I mentioned earlier, divided by 4 factorial. So this guy is going to look like 6 factorial divided by 4 factorial times 6 minus 4 factorial. Now let's extrapolate a general formula. Here, the n was the 6, right? That was the big set that I had from the beginning. I was choosing sets of size 4, so the r is going to be the 4. Not 4 factorial, 4. And so, in other words, i.e., the number of 4 sets is going to be equal to, well, n factorial over r factorial times n minus r factorial. That's a very important number. We call this a combination. The notation is very similar to the permutation notation, except instead of a big P, you have a big C. The notation here is C of nr is going to be defined as n factorial divided by n factorial r factorial times n minus r factorial, because I really used tuples to help me figure out how many sets there were. That is also now an important formula. Now at this point, and what I want you to realize this is the number of ways to choose R objects from n objects in no particular order. I just want a random group of 4 things from random group of R things from n things. In fact, C and R is often read N choose R. Now, other notations. You might see, like I said, N, C, and R. You might see N, C, R. You might see C, and R. You might see C, and R, etc. And by the way, the permutation notations, you would also have variations on that. NPR, you might see P, N, R, etc. Right? So these are multiple common notations. So what I want you to do at this point is find that notation on your calculator. Make sure you know how to get these numbers. And to make sure that you know how to get these numbers, let's just actually do an example. Tell me what is P of 16(3). In other words, that is the number of ways that I can take 3 objects out of 16 objects and put them in order. What is C of 34? Choose 7. So if I have 34 things, I want to pick 7 random things in no particular order. How many possible ways can I do that? So take this time to make sure you know how to actually do that on your calculator. The long way would actually be to put in the factorial so you can know how to find factorials on your calculator, but most calculators, including the ones that I recommended to you, will have a button that says one of these things. So make sure you can find it at this point. And in the meantime, I will look up. What I also want to tell you is another notation for this. Sometimes you write it like this. There's no division sign, so it's just one elongated parentheses. You put the top number here, the bottom number here. It's the same. It's the same. It's very common for when people are writing things down. It's very common to express like that as well. And if you're on Wolfram Alpha, you can actually type in this thing and it'll know what you're talking about. In case you're on a physical laptop or something. You can type in the parentheses thing. You can even type out the word N choose R. You can type out 34 choose 7 without the quotations, and Wolfram Alpha will know what you're talking about. So that's also nice. Okay, did everyone find it? What did you get for the P? £3,000. 3,000? Does everyone agree? Yeah, that's what I got too. Okay. What did you get for the 34? choose 7s? Huh? 16? It's a lot of ways. It's a lot. You wouldn't want to count that individually. Yes. So make sure you know how to get that on your calculator. That is going to be very important. Anything else I want to mention as far as theory goes with counting? I don't think so. So what we're going to do now is let's do some examples. Let's put what we've been learning into practice. We're going to do some counting examples. Yes.
About my calculator.
Oh, you know how to find this?
I don't think I see it.
Okay.
You got
Oh,
PRB? Okay, let me know.
You got one.
Yeah, good. Thank you.
So PRB stands for probability, and you can scroll to choose it. So with these, I think what you normally do is you put in the number first. So you put in 34, then you choose that, then you put in the 7.
Yeah. Oh, okay, thank you.
And if that's a part of another major formula, you'd actually put all that in parentheses. So you open parentheses, 34, PRB, selected, 7, close parentheses. And you can multiply that by other stuff. So we are going to get through all of these. And of course, again, I'll post an electronic copy of this. So counting examples. So we're going to put together everything that we learned from counting. So let's go. Problem 1. Let's suppose you have 3 shirts and 2 pants. How many possible outfits can you create? Yeah. 6. Why?
Okay, because you can do it with 3 shirts, 1 pants, and 3 shirts with another.
Sure. What scheme are you thinking? Why 6? Because I assume what you did is you multiplied them. Right? That's how you got the 6. What would tell you to multiply? Anyone?
Multiplication rule.
Multiplication rule. So, in other words, when I spoke about before experiments and stages, you want to take those terms very loosely. Sometimes you can think of almost anything as a stage. You can think of getting dressed as the experiment. This experiment will have 2 stages. So here's how you're going to think about it. So you're going to think getting dressed. That is your experiment. And now you're going to say there are 2 stages. So one stage is to choose a shirt. The second stage is to choose a pant. Does anyone use pant? I don't know. You always say a pair of pants, right? Yeah.
So you choose a pair.
Choose a pair of pants. Right? So you can think of the getting dressed as an experiment in which you're doing stages. Now, you are going to want to, you'll get used to this after a while, but you definitely want to, anytime you're thinking about counting, don't just say, I'm going to try to think about counting. Say, what am I using to count? It's either going to be the multiplication rule, it's either going to be a permutation, it's going to be a combination. Whatever you're looking at, you have to envision it in one of these schemas, right? Don't just start randomly stringing numbers together, because then you're going to multiply and add stuff when you shouldn't be doing it, because you're not really knowing what you're doing. Whatever you're reading, you envision it in terms of, in the context of one of the things that I listed before. So, I would think of this as stages in an experiment, which is getting dressed. And I know in the first situation, I have 3 choices. So there are 3 possible outcomes for the way the first stage is going to happen. And there are going to be 2 possible outcomes for the way the second stage is going to happen. The multiplication rule tells us that there are 3 times 2, 6 outcomes. And here, our outcome is us getting dressed. So there are 6 outfits. Alright, that's the first example. Now, of course, in general, you don't have to write out all this. Chances are, if at any point you need to know something like this, it's just going to be something that you know is 6 right off the bat. But I want you to be a little bit more deliberate in your thinking, because it's very easy to get mixed up. The problems can start to get really confusing really fast once you just start randomly moving numbers around. There has to be a reason why you're doing something. Every time you're multiplying numbers, you have to know specifically, why am I multiplying? Why am I allowed to multiply? What does it mean when I'm multiplying? Okay. So that is problem 1. Not too bad. Let's keep going. You toss a fair coin 3 times. How many possible outcomes are there? Well, how do you think about this one? Yeah.
6.
6? Why 6?
Because you're doing the experiment 3 times and there are only 2 possibilities.
Okay, so why 6? Explain how you get to 6.
Using the multiplication rule.
Okay, so tell me what are the stages in your thought process?
So when you toss it the first time, you can either get heads or tails.
Okay.
And then
So what are you thinking of the stage? Define the stage in the way you're thinking about it.
like the first toss.
The first toss is a
Is
stage.
it?
So this experiment has 3 stages, right? So this is the stage 1 is first toss. Okay, so now stage 2 is going to be the second toss. Stage 3 is going to be the third toss. Okay, now go back through that. How many outcomes can happen in stage 1?
You can either get heads or tails.
Okay, so that is 2 choices here. Second one,
You can either get heads or tails.
same thing, 2 choices. And third, of course, 2 choices. How many total choices?
6.
8, right? Multiplication rule, you're going to multiply them. So this means there are 2 cubed equals 8 total choices. And there is a way that you could actually list these easy. When something has 2 outcomes, well, you can actually generalize this idea, but you can create a table. Other ways to visualize. So I could envision this as the multiplication rule and just think of each toss as a stage. Or I could think of a table where if there are only 2 options, what you do is you're going to alternate. Now, there are going to be 8 alternations, or 1, 2, 3, 4, 5, 6, 7, 8. Now we know there's going to be 8 alternations, but how you can know is that eventually you'll notice that repeats start to happen. But the multiplication rule is going to suggest to you that there are 8. What you can do is you can start with tails and alternate every 1. Then move one column over, alternate every 2. Then move over, alternate every 2 squared, or every 4. Etc. And you will notice that is all possible arrangements of t's and h that can happen in 3 positions. So that's one way you can do it. Another way you can visualize it is another way. These will all come in handy later. It's by something called a tree diagram. Basically, a point represents the beginning of everything, and then you can again, this is very light here, you're imagining here. There's a possibility for what's happening in stage 1. There's going to be a possibility for stage 2. There's going to be a possibility for stage 3. And here's how it's going to happen. Well, in stage 1, there are 2 possible outcomes, so it can go boom or booms. You draw a branch to represent an outcome. You can either get heads or tails. Now, assuming this outcome happened, you're now here, you now have 2 possible outcomes. So from there you can get heads or tails. The same thing will be true if you ended up in this position. You would have 2 outcomes, heads or tails. Then each of these points, if you're in any of these positions, they will also branch off into 2 possibilities. Right? This thing is called a tree. So you can get heads, tails, heads, tails, heads, tails, heads, tails, right? Notice that at the final stage, how many positions there are is the total number of outcomes. There are 8. What does each experiment look like? Well, you go along the arms of the experiment. This represents the situation if you got a heads first, then a heads second, then a heads third, or a heads first, a heads second, then a tail third, or heads, then tails, then heads, or heads, then tails, then tails, then, or tails, then heads, then head, tails, then heads, then tails, and each arm on this tree represents one possible scenario, one sequence of events. And in one of them, Thanos snapped and whatever. Okay. So many ways you can visualize it, but at the end of the day, the multiplication rule is going to be your intuition here. Because you can think of a coin toss as some stage in an experiment. So, getting got a lot of mileage out of that one. Okay, so let's move on to 3. Any questions on any of the ideas I just presented? You toss 2 fair 6-sided dice. How many possible outcomes? 36. So toss 2 fair dice. Number of outcomes. What you can do, probably the nicest way to think of this, the most concise way, is stages in an experiment. Think of the stage 1 as the outcome of the first toss, outcome on the first die. Singular for dice. And the outcome of second die. Now, of course, in the first one, there are 6 choices that you can make. In the second one, there are 6 choices. And so the multiplication rule, there are 36. 6 times 6 equals 36 total choices. So there are 36 outcomes. A very common way to think about dice in particular, because this example comes up all the time. One thing you'll notice with probability is that gambling comes up a lot. Take any book on probability, they're going to talk about poker and bridge and playing dice and all that kind of stuff. Not just because of fun, making fun of things, but that's historically accurate. Probability was a branch of mathematics that was purely motivated by gambling. That's how it came about. You know, because gambling was a very famous pastime back then, and people wanted to know, how can I get an advantage over someone else in this game? And then they asked mathematicians to talk about possibilities and what are the chances that I'd be in a better possibility than this guy. And so, yeah, Fermat and Pascal were the first mathematicians to really start to delve into these kinds of questions, and probability was born. So it was born out of gambling. So that you'll have a lot of examples that are going to be with playing cards and dice and all that stuff. So there's a common way that we can represent the outcome on 2 dice, and that's by a table, where you kind of split along die 1 and die 2 with the possible outcomes, like it could be a 1 or a 2 or a 3 or a 4 or a 5 or a 6, and going down is a 1 or a 2 or a 3 or a 4 or a 5 or a 6, and you can create a table like this. Inside the table, so these are the table headings, so these are not part of the table. One thing you'll notice now is, and this is like a picture representation of what the multiplication rule is actually saying. It's kind of like you're finding the area of a square when you take one number of outcomes times the other ones. So it'll be 6 by 6 possibilities. And one possibility is that die 1 gives you 1 and the other one gives you 1, or it could give you 1 while the other gives you 2, or it can give you 1 and the other gives you 3, and so forth. Or this can give you 2 and that gives you 1, this can give you 3, that gives you 1, this can give you 4 and that gives you 1, so forth. And then it will be like 2, 2, and here of course is 3, 3, and so forth, all the way down to 6, 6, and you can fill in the rest, right? Now, every now and then they might ask a question like, oh, what is the possibility that the sum of the dice is going to be blah? In which case, in the boxes, you will instead fill in the sum. Or what is the possibility that the difference in the dice is blah, blah, blah? Then you fill in the differences. You can actually fill in this table with whatever function of the number of the dice is being asked about. So that's a very common way to represent 2 dice being tossed. And that's surprisingly a very common question to ask about, because, yeah, probability is all about gambling. At least it wasn't. So, 36 total possibilities. Number of 10-digit phone numbers. First number, a 1. No other restrictions. How many? Billion. That's a lot, right? We spoke about how long it would take you to count to a billion. If any of you started when you were born, you wouldn't finish yet. So we don't want to actually do that individually. But we can apply the multiplication rule to 10 stages. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can have number of outcomes per stage. Well, stage 1, there's only one possible outcome. Literally, it has to be the number 1. Now, after that, you have 10 choices, because you can choose any of the digits between 0 and 9. So there are going to be 10 choices here, 10 choices there, 10 choices here, all the way down to 10 choices at the end. And the multiplication rule says there are 10 to the 9 total choices. So you can think of a phone number as a 10-stage experiment. Let's get to some of the challenging ones. The ones toward the end are more challenging. These are just to kind of illustrate the thought process, get you used to thinking in this way. Okay, back to pose. You have 3 work shirts, 4 work pants, 2 jackets, 4 ties. Your office dress code requires that you wear a shirt, pants, and jacket, or you can wear a shirt, pants, and a tie, or you can wear a shirt, pants, a jacket, and a tie. And they don't care if you wear shoes or anything. How many possible work outfits can you create? Think about it. Come with a number. Tell me the number. Are you raising your hand?
Yeah.
Oh, so you're going to tell me how to do it?
Yeah, it's just multiplication
Okay,
for
tell me how
all.
to apply
So
it.
3 times 4 times 2 times
3 times,
3. Oh, sorry.
huh?
No, I need to reread the
Oh,
question.
okay. Yeah?
So you find the number of possible like combinations for the first combination that they gave you, the shirt, pants, and jacket.
Okay, shirt, pants, jacket, okay.
So you can have there are 3 possibilities for shirts, 4 possibilities for pants, and 2 possibilities for jackets. And you multiply them.
Okay, so how many possibilities?
24.
24 possibilities here. Okay, then,
Then you have a shirt, pants, and tie. And the possibilities are 3, 4, and 4. It's 48.
okay,
And then you have shirt, pants, jacket, and tie.
okay.
Which is 3, 4, 2, and 4.
3, 4. 3, 4, 2, 4.
And that's 96.
Okay, so what are you going to do?
I don't know.
You add them up. How many possible outfits? 160. 168. This represents another principle. Not only can you know how many outfits you can create without like trying them all on, you know we can make 168 possible outfits, but it illustrates an important principle. These outfits do not overlap, right? Each one is a different kind of outfit, right? And so this shows adding multiplication rule counts when you have to have all things happening at the same time. So you have to wear a shirt, pants, and a jacket all at the same time. When it's happening all at the same time, multiplication is what you're thinking. When you have an or, like it could be this, or that, adding might come into play. Adding would represent the exclusive or. So you want to add when you're trying to figure out or, but there's no overlap. If there's or with overlap, that's different. So let me make sure I emphasize that. Adding helps you calculate or count the exclusive or. If this or that or that or that can happen, none of these will ever overlap with the other. I can figure out the total number of possibilities by just adding up all those individual possibilities separated by the or. And I'll talk about this later, but you can think of and as multiplication in the case where things are independent. One doesn't have to do with the other. Which is kind of behind the multiplication. Okay, so there's 168 possible outputs here. Making headway. Consider all possible 3-digit numbers. So you can go from 0, 0, 0, we're including all zeros, to 999. 99. How many with exactly 1 digit greater than 5? I'd like you to figure that out without literally listing all the possibilities. Yeah, Ben?
I got 972, and I got that. So like, there are 4 digits greater than 5. So then I'm left 4 times 9 times, or 4 times 9 times 9.
Okay.
So then that number won't go up by 3 because it doesn't really matter because like it's gonna be the same situation as 9.
Explain, what do you mean?
It should be like 4
So
times 9
let's write out the first situation you're discovering, talking about.
Yeah, so the first one, like for the first digit, there would be 4 options because it's 4 digits greater than 5.
Oh, so you're talking about the first digit. This is the one greater than 5.
Yeah, so like in that
In
scenario.
first digit.
Okay.
And then the other two can be.
Yeah, well then like you can just multiply that by 3 because you know, it doesn't matter what order you multiply things, it'll be the same.
Yeah. So another situation is when you have those 3 digits, but the second one is greater than 5.
Yeah.
Another situation you could have, and this would be the last one, is that the third digit is greater than 5. So, how many choices do we have here greater than 5? 4. So that's the 6, 7, 8, 9. So there are 4. Now, right, so we only want 1 digit greater than 5, which means all the others must be less than or equal to 5. Right? Yeah, it says exactly 1 digit. So you don't want any other digit to be greater than 5. So how many ways can we be less than or equal to 5? That's going to be 6. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. So that's 6 choices. And I'm not counting the digits here, I'm counting the choices. Pretty much any time I'm going to write that. And then here there would also be 6 choices. Now you can take that same reasoning. There are 4 possibilities here, and 6 here, and 6 here, versus there are 4 possibilities here, and 6 here, and 6 here. And this is why he decided to think about one situation and multiply by 3, because he kind of realized that this will kind of pretty much be symmetric. Symmetric is the wrong word. But it'll be very similar to the other situations. You have the same numbers in play being multiplied. So you could actually just figure out one situation and multiply it by the number of situations you want. In fact, when I was explaining the Monty Hall problem, I kind of used that idea. I wrote down 3 possible scenarios on the board, when in fact there were 9, but by me explaining the 3, it kind of extrapolates to the 9 automatically. So this, how many here? 144. So this would also be 144. That would be 144. Now, this is an exclusive OR, because if I want the 1 digit that's greater than 5 to be in the first, it cannot overlap with it being in the second, and so on and so forth. So there is no overlap, so I can add. And so how many? 432. There are 432. Now, how many possibilities were there in total? 10,000, right? There were 10,000 possible 3-digit numbers. Or 1,000. Now, it turns out that a little less than half of those will have at least exactly, we'll have exactly one digit being greater than 5. And we didn't have to write down all 432 numbers to figure that out. Simply cleverly use the multiplication rule and adding the exclusive OR. Questions on this one?
Well, 10,000 now.
Huh?
10 to the third power.
10 times, it is 10,000.
Isn't it like 10 to the third power?
Yeah, which is, what?
Like 10 to the third power? Right, like 10 to the third power.
If we're talking about all the possible 3 digits, then yes, it's 10 to the third power.
Okay,
Right.
that's 10,000, not 1,000. Like,
All possible
10 times 10 times 10.
3 digits, numbers. Well, think of that as a 3-stage experiment. There are 10 choices, 10 choices, 10 choices. Multiplication rule tells us there are 10 to the 3 choices, that's 1,000. Right. And then a little less than half of those will have exactly one digit being greater than 5. And to segue to like probability, if someone were to ask you, what are the chances that if you put all these 1,000 numbers in a bag and you put your hand in and you shake it up and you pull one out, what are the chances that the number that you're looking at on that piece of paper has only one digit greater than 5? Well, the chances would be 0.432. 43% of the time you run that experiment, if you do it over and over and over again, 43% of the time you will be in this situation. But that's comes later. That's probability. Okay. So I think we can get through this one more example. I guess we'll leave the last one for next class. So here we're going to talk about cards. I kind of described them for people who don't know about cards. So there are things called the kind of a card. You can be an ace, or 2, or 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10, or something called a jack, or a queen, or a king. There's a card called a joker, but it's often left out of the game. There are 2 jokers. Now for each of these cards individually, they have 4 what we call suits. So you can have an ace of diamond, that's one possible suit. You can have an ace of hearts, that's one possible suit. You can have an ace of clubs, looks like a clover, that's one possible suit. You can also have an ace of spade. Spade is a fancy name for shovel. Like a shovel that you're digging up dirt with. Okay, so you have 4 possible those. So you can have a card with an A on it and that, and a card with a heart on it, an ace, and a card with this, and a card with this. Okay? And so you have 13 possible kinds, you have 4 possible suits, so you have 52 total cards. Joker cards are on the stairs in the Bronx. So now, this is called a card deck. So I assume everyone's seen cards. You can shuffle them and you can play games with them. Okay. So now let's talk about poker hands. So say you're playing 5-card poker. So you're going to play a game where someone shuffles the deck and they randomly deal you 5 cards, and based on what's on those cards, you can say you are better or worse than someone else with another set of 5 cards, according to certain rules. The rules, by the way, of poker are set up according to probability. The lower the probability of you getting a certain arrangement, the higher value your card is because it's more rare. So we're going to kind of count the kinds of card hands you can have, or one particular kind of card hands. So first, A. You're dealt 5 cards. How many possible hands? 5, you think a combination. Why a combination?
What matters?
Its order does not matter here. So if someone gives you like a jack of diamonds and an ace of spades, it's not going to make a difference whether they first give the ace of spades, then the jack of diamonds. At the end of the day, you pick up the cards that are in your hand, that's your card hand. So the first thing you're going to want to realize here is that order does not matter. Now, once you've identified that, it means you're probably not going to want to think in terms of stages like, not always, but that kind of hints to you that you're not going to want to think of something as being in the first position, in the second position, third position. That's not how you want to think. How you're now going to think is that there were 52 things, and someone is giving me 5 things out of that 52 things, and the order in which they're giving me does not matter. That screams combination. This is C of 52, choose 5. Or in other words, 52, choose 5. How many are there? Yeah.
2,598,960.
Is that? Does everyone agree? Do me a favor, divide that by 365. 7,120. So, 7,120. So if you were to play 5-card poker every single day, a year, once a day, and let's even assume that you get a different hand every single time, how long is it going to take you to get the same hand again? 7,000 years. There are a lot of poker hands. Now you wouldn't want to have to count that individually. That's a lot. Okay, now let's talk about something called a full house. There's a hand in poker called the full house. Basically, it's when you like say, okay, there's a family of 5, there are 2 parents and 3 children. That's called a full house. So basically, there are 2 parents, 3 children. And it's separated, denoted by different kinds. Okay. So here, these 2 are of the same kind, and then you have 3 other cards that are also of the same kind, but of course different from the kind of parents. So for example, you can have 2 kings, maybe a king of hearts and a king of spades, and then you can have 3 threes, maybe a 3 of diamonds, a 3 of hearts, a 3 of clubs. So you randomly deals you a card, you lift them up, and you notice, hey, I have 2 of one thing, one kind, and 3 of another kind. This is said you have a full house. How many full houses are there? How many ways could you get a full house? Okay, go. How would you think of this? I guess we have to think about it next time. Time is actually up. So think about that, and we'll pick up with that next time. And you can also think about the following problem, problem 8. We'll run through that. After this, I think we have enough counting in Georgia to deal with probability. Can I do that?